But now we have Gail Shaw with intelligent query processing.
Sweet, thank you. Now I can actually get started. So not digging, Andrew, stuff slips. And Erin and I were kind of making a nuisance of ourselves. So moving right on. This, I hope, is an advanced enough session for this conference, because it wasn't written for this conference. This was written for actually past Summit, 4 or 5 years ago, and I've updated as we go along. So what I'm going to be talking about tonight was what was introduced in SQL Server 2017. That would make it 3 years ago past Summit, because it couldn't have been 4 years ago. Time flies these days. What was originally called adaptive query processing, but was quickly changed afterwards to be called intelligent query processing. This is the ability of the query processor, in some cases a query optimizer, to identify particularly problematic portions of queries and to treat them specially. So let's start with the problems. The problems, and these are very familiar to anybody that's done query tuning for SQL Server. The problems are that bad row estimates cause incorrect row estimates, bad row estimates, cause bad performance. Horrible problem. We've probably seen this multiple times. The second problem is that multi-statement table-valued functions and table variables cause bad performance, to the point that I will often suggest to somebody, if they've got a performance problem with a piece of code that uses table variables, try replacing it with a temp table and see if that makes it better. And if it does, great, we're done. If it doesn't, then we'll actually dig into what caused the problem. Third one, inadequate memory estimations cause bad performance. And this is another quite problematic one. Adam Mechanics got a whole pile of very interesting presentations and tricks on this one. But for most of us, once your query is getting incorrect memory estimates, you've got bad performance and there's not much else you can do about it. And then lastly, scalar functions cause bad performance. I affectionately refer to scalar functions as developer pit traps, because I've seen so many developers run into them at high speed, not realizing that there's a problem, and get really, really, really badly burned and hurt as a result. So those are our problems. You can ignore what I'm keeping on screen. Those are our problems. And all of these are ones that adaptive query processing, intelligent query processing, in its 2019 version, address. Most of these were addressed in 2017 as well, not all of them. It took as long as 2019. All right, so let's go into this. Well, before we go into the details of the various options, why? Until SQL 2017, the optimize execute process was linear. A query was optimized, then a query was executed. And there was no ability for the query processor to go, I don't like this plan, it's slow, redo it. There were recompiles. There was something called a recompile, but this only happened in two cases. This happened if the statistics had changed prior to, if the statistics used in the generation of the plan changed after the plan was generated, but before it executed. Or if the schema had changed after the plan was created, before it was executed. Those were the only two times where the plan would be thrown out as invalid and regenerated. But even if that happened, those recompiles started before those recompiles occurred before the execution started. The process was fetch the plan from cache, validate it, and that validation is checking statistics changes, schema changes. If the plan is valid, run it. The query processor had no ability to, partway through execution, go, this nested loop was estimated to run 10 times. I've so far run it 10,000. This plan's wrong. the query processor had no ability to decide what to do. It took the plan, it executed the plan. If that plan was invalid for any particular reason, if that plan was inefficient for any particular reason, too bad, sucks to be you. I hope you enjoy waiting 20 minutes for this query to execute, because the query processor will simply run it. Because the optimizer estimates the rows, the optimizer chooses a join, the optimizer estimates the memory, and then the execution engine requests the memory, executes a plan, that's it. And it's that's changed with intelligent query processing. Not completely, not 100%, but in some places. So there are 4 aspects to intelligent query processing that I'm going to be talking about tonight. And they are adaptive joins, interleaved execution, memory grant feedback, and my favorite 2019 feature, inline scalar functions. Favorite for a couple of reasons. One being that it blows up quite badly in some cases. Let's start with the first of those, the oldest one, adaptive joins. Let me go back. Traditionally, if we looked at an execution plan, it had a nested loop join, a merge join, or a hash join. And which join it was chosen by the query optimizer based on the estimated number of rows in the outer table. And a few other things, indexes on the tables. There was more to it than just the row count, but the row count was one of the main ones. If the row count on the outer table was low, you got a nested loop join. If it was high, you got a hash join. And merge joins came in somewhere in the middle if you had the appropriate indexes or sort wasn't expensive or a bunch of other things. I'm going to leave merge joins out of this conversation because they actually don't feature in adaptive joins. Adaptive joins is about the hash and the merge. Sorry, the hash and the loop. Hash and the loop. I just said merge joins aren't part of this. With adaptive joins, and this, by the way, let me be clear about this. This is a SQL 2017 feature that is available in databases of 2017 compatibility level or higher. If you're running your SQL 2019 database in compat mode, and a 140, whatever is the compat modes these days, you are not going to see this. You will only see it on the higher compatibility levels. What an adaptive join does is defer the choice of join to after execution starts. The query processor, sorry, the query optimizer does not choose whether to do a loop join or a hash join. Instead, it puts in a placeholder and lets the query execution engine decide. And this is absolutely fantastic because what it means is that if the query plan was generated with 10 rows in the outer table, in the first input, that would be a loop join. If it ran later on 10 million, well, loop joins on 10 million rows aren't pretty because we're looping over 10 million rows. In this case, we haven't chosen the join type. So the query plan is generated with a placeholder in. If the first execution is 10 rows, it gets a loop join. If the second execution is 10 million rows, it gets a hash join. The query processor is allowed to decide which to use. And this is what it looks like. And I've seen some people really confused by this because this is the first time that we have ever seen a join operator in an execution plan that takes 3 inputs. Because joins in the SQL Server query processor and the query optimizer are 2 table joins. If you're joining 3 tables together, you get 2 joins, not 1. So in a SQL Server query plan, you only ever see 2 inputs going into a join. With adaptive joins, you see 3. So I'm not going to talk the limitations right now. I'm going to go and try and find my demo. I have it around here somewhere. Not that database. That database. All right, let's hope this actually works, because this demo is a little bit finicky. I have here a store procedure. And this particular join here between the shipment, these two tables, is one where I could get a lot of rows or I could get not very many rows. So let me just do some quick queries against my shipments table to make sure I know what I'm talking about. And I apologize, I should have done this in advance. I'll blame the work meeting that ran till 6:30. I want client ID and I want no schema qualified tables. Oh, I'm sorry. Nitpicky, nitpicky, nitpicky people. I hope we're happy now. Okay, so client 64 is apparently a very busy shipper because 7,006 shipments. And way down at the bottom, I have number 240 that's only got one. I'm not going to use 240. So 64 or 56. One of these days, I'm going to actually save the version of this demo that has all the numbers in it. Anyway, plan's been generated. Store procedure's been created. Let me execute this. It would help if I turn the execution plan on. So running this with 56, I get a grand total of 746 rows back. And thank heaven, I've got an adaptive join. It would be a great start for the presentation if it didn't go adaptive. It would probably be a bad compatibility level. Actually, on that point, let me show you how this works in old compatibility levels. I'm just going to go here. You should know how to do this, but I can't remember. This is somewhere. All right, so compatibility level, I'm going to switch this back to 130. Script this out so I can do it again. All right, so let me switch this back to 130. Wipe all my plans and find my adaptive joins again. All right, so I've cleared my plan cache. In old SQL, 2016 and before, client 56 gets a nested loop join. Nested loop join, actual number of rows on all executions, 746. Estimated number of rows was somewhere in here. Why can I not even see that? Let's go off this one, it's easier. Actual number of rows, 31. Estimated number of rows, 31. The loop join estimated to execute once. Yep, it executes. That's fine. This index seek was estimated to execute 31 times, actually executed 31 times. So this is actually correct. This loop join is going to loop over 31 rows. This is efficient. This is not so efficient. My index scan down here has estimated, hey, hash join. Why did you go to hash join? That's not right. Oh, what the hell? No. This is not behaving itself. I do not like demos that don't behave themselves. It's supposed to be 56. And this should have been that's a nested loop join, yes. So this should have gone. That looks more like it because it's slow as hell. Nope, gone to hash. Okay, this is fun. I do love a demo that doesn't work, and I don't know why. That's fine. Okay, so this is going to be fun if I can't keep a plan in cache for more than one query. Okay, I've got memory pressure. No, I've got memory pressure. Let me go kill some things. Not PowerPoint, that would be dumb. Close Word. Apparently I did not make the requisite sacrifices before I started tonight. Okay. Hopefully that'll clear my memory up a bit. This is weird though. This machine's got 32 gigs of memory. It shouldn't be having memory pressure problems. Yes, okay. All right, the memory pressure on the plan cache is fixed. No, Forrest, I had worse. I had Firefox. All right, so now I've actually got a plan that's stable in cache. So this index seek, estimated number of executions 31, actual number of executions 7,006. That's a problem. That's not fantastic. That's going to be causing problems. 7,000 rows, not so much. But if this was 7 million, this would be unpleasant and slow. All right, so now let's switch back to 160. I used to know these compat levels off the top of my head. Emphasis used to. 150 for 2019. All right. All right, so back to compatibility level for 2019. Now let me run this again. Right, and so we've got an adaptive join here. We've got our join, we've got our 3 inputs. Right, the way this works, the top one is the first input. That is the input that is read always before the join type is decided on. For those who are awed that I could fix this, I've had this problem before, so it's not a case of I was guessing. I've had that problem before in this presentation with this demo. This input is read. This input is read, and then the query processor decides which join we're picking based on this input. So 31 rows are read, estimated number of rows 31, actual number of rows 31. If we hover over the adaptive join, you will see actual join type nested loops. Nested loops, multiple of them. The decision was made by the query processor that based on 31 rows in the input table, we are doing a loop join. The second input you see is the one that is executed if a hash join is used. This input is not always run. This input is run when a hash join occurs. So if we look at the properties of this one, actual number of rows is 0. This input was not executed because we're doing a loop join. This index seek here, the third of the inputs, is the one that is executed if the loop type of nested loop is chosen. So this input, this seek, number of rows read, 746, that's the number of rows in the detail table. This operator was executed because we do indeed have a loop join. You can see that with the size of the arrows as well. No data flowed up that one. Data flowed up that one. So the key for a loop join, yeah, Hugo, shush. The input for a adaptive join, the key to understanding an adaptive join is that one of these is executed, not both, never both. And yes, Hugo's entirely correct. Look at the number of executions. This one is showing 0 executions. It was not run. This one should be showing 31 executions. 31 executions. This one was run. All right, so let's go and pick my other client. That's the 64, the one with lots and lots of rows. And I run this one. We have got exactly the same plan. We've got an adaptive join. 7,000 rows in this one execution. And if you look this time, the second input is the one that's been executed. It's been executed once. It's a scan. It will only be executed once. It should only be executed multiple times if I've gone parallel. The index seek has got 0 executions. It's not getting run. And then if we look at our join type here, actual join type, hash match. I've got a hash join here. And I note I'm still getting recompiles. I shouldn't be, but I am. So that's going to make the rest of these demos quite amusing. But you can have a look at this. You can now see this has done a hash join. It has not done a loop join. I'm not entirely sure where the input stores those rows. It probably is in a spool somewhere. But yeah, so the downside of this is that this input has to be read entirely before the join type can be chosen. So what we've got here is actually a blocking operator. Nested loop joins normally are not blocking operators, but adaptive joins are. I'll take that over waiting 3 hours for a query to execute because we got the wrong bloody join type. All right, let me move that out of the way. So requirements, there are requirements. Move that out of the way as well. This doesn't work in every case. Adaptive joins cannot be used on every single query. The limitations requirements. So batch mode, it requires batch mode. You may have noticed, I've got column stores here. I use column stores intentionally. This demo is from these demos were initially written for SQL 2017, where you could only get batch mode if you were using a column store. So I still use a column store, but if you look, I am actually running in batch mode. So the query, this requires batch mode or no adaptive joins. The query must be executable with an indexed nested loop join and a hash join. In other words, no unindexed nested loop joins. We're not going to be doing scans and spools or any other weirdnesses that you can do with nested loops. We are not doing merge joins. If a join is chosen as a merge join, it is not adaptive. It will not be adaptive. And the query plan shape must look identical for loop and hash joins. So going back to my 130, if I ran these two, so my plan on 130 was an index scan, ignore the filter because it can get pushed down into the scan. Hash match, it's a particular shape. And if I switch this to 56, I intentionally want recompiles this time. It's the same plan shape. So that's another requirement. The plan shapes must be identical other than the type of join. So that is adaptive joins.
Hey, Gail, we have one question on adaptive joins that I don't know the answer to off the top of my head, and it is, adaptive joins make sense for data with non-uniform distributions. Are there criteria where the query optimizer chooses not to do an adaptive join? And I think you kind of covered that,
absolutely.
But yeah.
Well, other than the restrictions, which are an obvious one, I mean, if it doesn't match these, no join, no adaptive join. Other than those, I don't know, to be honest. I'd actually have to go and bug JoSec on this one because I don't know. The thing is, this doesn't just work well with non-uniform data. This works really well when data is changing. So the biggest problems I've seen in the past with the wrong join type being chosen was on the older ascending key problem, where the data was loop join, loop join, loop join, loop join, too big for a loop join, but we've got the same plan. Oh, hell. The data wasn't non-uniform. It was perfectly uniform. It was just growing over time, and we got the wrong plan as a result.
And then we have one more question. Does this mean that it matters for adaptive query? Wait, does this mean that it matters for adaptive queries on which side the table is placed when using it?
No, it doesn't. Again, order of tables in the query has got nothing to do with the order that the query optimizer puts them in. It doesn't care. The query by the time the query reaches a QO, that's gone anyway. It's been parsed out. So no, absolutely not. Fortunately, let's not do that. Okay,
Cool.
So let's move on to interleaved execution. Cool. It took me half an hour to do the first one. So how many hours do I have? I'm kidding. I'm kidding. These are actually faster. All right, interleaved execution. Multi-statement table-valued functions are a problem, or were a problem, because we couldn't get an accurate row estimation of them. So that was where the estimate of 100 rows came from. We estimate 100 rows because how many rows? Absolutely no bloody way to tell. None whatsoever. Because the table function hadn't run at the time that the query optimizer optimized the query, and hence it can't get the row count estimate because there isn't one. And so we get that silly 1 row, 100 row table variable estimate, one row in the old CE, 100 rows in the new CE. That was how it used to work. With adaptive query processing, intelligent query processing, what happens is that the execution of these two is split. Instead of parse, bind, optimize, execute, it becomes parse, bind, optimize, execute, optimize, execute. We optimize the table-valued function first, the contents of the function. That then gets executed. The results of the table-valued function get put into a table variable. Once the function is complete, the outer query is optimized. It hasn't got a plan yet. It now gets its plan. At this point, we know exactly how many rows were returned from that table-valued function because we've already run it. And so we can generate a plan based on the actual row count, not a 100-row estimate. So let's have a quick look at how that one works. So the question quickly on Slack, I'm kind of keeping an eye on Slack, you've probably guessed. Adaptive query processing actually wasn't fine because a lot of the newer features are not adaptive at all. There's nothing adaptive about them. Adaptive was great when it was things like the adaptive join, but intelligent query processing is a larger category, to be honest. All right, so functions, interleaved execution. Where are my functions? Sorry, long database again. All right, so I have a really weird little function here. Oh, no, don't tell me oh, crap. I did a demo last week and I dropped a table and I forgot to restore my database after that. So I'm just going to have to apologize and do a quick restore and talk through it. Talk through something so you don't notice me restoring databases in the background. I promise I was prepared for this, really. Okay. All right, while that's running. Let me talk about deferred compilation and then I'll demo the two of them together. I've put these in a single section of this slide deck because they are kind of the same thing. So to be clear, interleaved execution, SQL 2017. This was added in 2017. In 2019, they also added what's called deferred compilation for table variables. And they're kind of the same thing. The whole idea here is that we don't optimize and then execute a query that uses a multi-statement function or a table variable until we know how many rows will be returned by that multi-statement function or table variable. So when we've got a multi-statement table valued function, we split the execution, interleaved execution. We execute the function first. dump the results into a table variable, then compile, optimize the query that uses that function to and execute it. With a table variable, we defer the compilation of the query that uses the table variable until after the table variable has been created and populated. In other words, right before that query executes, which means we now know exactly how many rows are in that table variable because it already exists. And so we don't have that one row estimate. And by the way, this slide's actually wrong. The 100 row estimate never happened for table variables. That was for functions. Please, pretty please be finished. Not quite. Yeah, I hate these. All right. So to be honest, if you look at the plan, there's nothing particularly interesting. You can't see that you've got interleaved execution if you look at the execution plan. Not easily anyway. Please be finished, not finished. Oh boy. Because I can't exactly run a query that uses a transaction table if the transaction table doesn't exist. By the way, I was demoing SQL injection, and I very intentionally dropped my transaction table as part of my demo of SQL injection. I will let you know that my demo of SQL injection was very effective. I just forgot to restore the damn database afterwards. Anyway, let me talk you through what this looks like. So we've got a function, that shipment total, and this function will look a little weird to those of you familiar with multi-statement functions. But yeah, so it returns a table. There's my table definition, all my stuff here, and here's the query that uses it. Now, why I say this looks a little weird is because this isn't on apply. This is joined. I'm joining this function in. This is definitely an odder use for a table value function. And when I finally get a database back, I'll explain why. So my second, All right. I probably should not have done that. All right. Let me talk about limitations while I'm waiting for this backup to slowly restore. Is this a case of the watched kettle never boils, the watched restore never finishes? Requirements.
We do have one question I can ask you while we're waiting.
Okay. Yeah.
If we have to stream all the records to the adaptive join in order for the execution engine to know what join to select, does that mean it requires a memory grant, which could be huge, which would be strange for a loop join?
Yep, it does actually require a memory grant. As Hugo noted earlier, and thank you, that was the perfectly timed question. It's a hash table. It's a hash. It's literally a hash table in memory. Yes, it does indeed require a memory grant, and with all the caveats of that. So yeah, adaptive joins are not as fast as a nested loop join would be. They're not as fast as a hash join would be. Their benefit is they're adaptable. Yay. Okay. Whew. Now it's working. Okay, let me set my compat mode back firstly. If I run this is running in compat mode 130. This is SQL 2016. If I go and look for my table valued function, and please ignore my missing indexes. I know they're missing. I don't care. My table variable, my function is somewhere around here. Estimated number of rows to be read, 100. This is a table valued function. 100 rows estimated because how many rows is it going to return? At compile time, we don't have this vaguest clue. Let me switch this back to 150. And we'll note the massively, incredibly different plan. No, it's exactly the same plan. Honestly, there's nothing you can see in the plan that's different, with the exception of estimated number of rows to be read, 2,627. We don't have that 100 row estimate anymore because we knew exactly how many rows the function was going to return because we ran it before we generated the plan for that query. Now, one of the limitations of this is according to the documentation. Firstly, read-only statements. selects only. If you're planning to use a multi-statement function in an update or delete, I'm sorry, firstly. Secondly, you're not going to get interleaved execution. It's only for selects. Secondly, the documentation states that it may not be used on the inside of a cross apply. Okay, cool. So here's another demo. Here's a function. Oh, come on, crap. Would help if I actually highlighted the whole thing. And I have a cross apply to my function. This is on the inside of a cross apply. So according to the documentation, this does not get an adaptive join. Execution plans are useful. But if we go and have a look here, actual number of estimated number of rows. Is that right? Is that right? Well, yes, it is because duh. Well, of course, it's going to be 100 rows because I put 100 rows in here. So let's try something a little larger. Estimated number of rows to be read 1,000. This is an interleaved execution because it doesn't have the 1,000 rows. So the 100 rows. We make that even clearer. This is an interleaved execution. It's also on the inside of a cross apply. So is the documentation wrong? Actually, yes, it is. The number of executions must be determinable at optimization time and deterministic. If the documentation has changed, I'll have to fix my slides. What it means is that the optimizer must be able to work out how many times this function runs. And it must be able to work that out at optimization time. And it must always be the same. So if I did this, which is weird, but it'll work. This is now no longer interleaved, and my estimated number of rows per execution is back to 100. So I've lost my interleaved execution. I don't have a demo for table variables, but it's pretty trivial. So what I could do here is no, not values, not values, not values, not values. Kind of weird, but it works. And if you look at this, I should have here estimated number of rows to be read 265, not the one that you would expect and the one that you would get on earlier versions. I switch back to 130 compatibility level and run exactly the same thing again. My estimated number of rows, that one. Estimated number of rows to be read, 1. That's your table variable estimation. On 150, we had 256. Well, that's not going to work, is it? Because of the deferred compilation for table variables. If we run that now, this is back on 190. Sorry, on 2019 compatibility. My estimated number of rows to be read from my table variable are 265, not 1. Okay, so any questions on deferred compilation or interleaved execution? And by the way, I glossed over deferred compilation, but I did put 2 posts on my blog quite recently, this year, in fact. Actually, no, last year. One was last year, on deferred compilation and table variables. So you can go and have a look at those if you need. Joe, any questions? I hear silence, so apparently no questions.
It's because I was muted. We had one on recompilation, and I just answered it live.
Cool. That's a nice thing about having a moderator that knows your topic. All right, moving on. Memory grant feedback. This one is complicated. This one, oh boy. All right. Queries that use hash tables, that's a hash join or a hash aggregate, spools, a bunch of other query operators need memory grants. It's a piece of working memory a piece of memory that is used for the query. This is not the buffer pool. This is not the plan cache. This is a little bit of memory that the query needs in order to do stuff, interim results. The memory grant needed is calculated by the query optimizer. How? It guesses. Look, it guesses pretty well because it's based on row counts, estimated row size, a whole bunch of heuristics, and any one of us who have been optimizing queries for a long time knows that it gets it right a good amount of the time, but when it gets it wrong, oh damn, does it get it wrong. And the problem is there's no way you can hint a query to say more memory, please, less memory, please. I mean, you could do some complicated tricks. Adam's got some astoundingly weird query constructs that you cross-apply a whole pile of stuff into a query that returns no rows or no columns, but convinces the optimizer to estimate like 2 or 3 gigs of memory. It's impressive, I must say, but it's really a hack. Now, if the query requests too much memory, then you're reducing concurrency because there's only so much working set memory. And queries that request a lot of memory often have to wait to get that memory. If anyone's ever seen resource semaphore waits, that's a query waiting to get a memory grant. Queries that request too little memory spill to disk. So yes, there's a hint max grant percent. Yeah, kind of, not really. You can encourage it. It's not, you can't tell the optimizer twice the memory that you think it should need. It doesn't unfortunately work that way. So yeah, 2 queries that request too little memory, spill to tempdb. Potentially spill multiple times. I recall, I think it was Paul Randall, had a particularly pathological query once that he had written that spilled to tempdb like 60 times during its execution. It was horrible. It was horrible. Look, he wrote it to be horrible, but it still was horrible. So both of these are problematic. Both of these are actually really annoyingly hard to fix. Until we got to 2017. This one, so the previous intelligent query processing features have all been on the same query. Adaptive joins lets the processor choose which query it's going, which join type it's going to use. Interleaved executions, we split the optimize execute in pieces. Memory grant feedback, however, applies across the executions, across multiple executions. And this is why I'm hoping my plans stay in cache, because if they don't, these demos are going to break horribly. So what happens here? Actually, let me demo this. It's easier to demo this, and hopefully my demos work. Please, demos work. Please, please, please work. All right, so I've got a really weird query here. If you're wondering why you'd ever write a store procedure like this, you wouldn't probably. But I've got a filter on priority. Priority in this database is a number between 1 and 3. And if I'm not mistaken, this works. So, yeah, 150. Okay, so if I run this the first time, it's going to return no rows. That's fine, because there's no priorities that are less than 0. So this database doesn't have any. And I've got a warning on my select, on my query plan. Warning, the query memory grant detected excessive grant, which may impact the reliability. Grant size initially 67 67,000 megabytes? That's a pretty large grant. So what's that? 67 megs? Yeah. 68 megs of memory. It used less than 1 meg. Now, if this was SQL 2016 or earlier, the next time I ran this query, it would request 67 megs of memory, and the third time it would request 67 megs of memory, and the fourth time it would, and so on and so on and so on. Right, let's hope that everything's working. Everything's not working. There we go. Okay, so something's still flashing my plan cache, so I need to run these things quickly after each other. The second time I ran it, let me actually do that again so you can see. Actually, what the hell is running on my machine? Oh, come on, seriously? That can go. This is ridiculous. So, well, less than 30% of my memory is in use and SQL's dying. Okay, fine. Maybe that'll fix it. All right, let me try this again. So the first time I run it, we've got a memory grant, memory grant warning, excessive grant. Second time I run it, it's gone. Let me show you the difference. Let's switch back to 130. And SQL prompt. All right, this is 130, so this is compat mode 1 for SQL 2016. Excessive memory grant. Excessive memory grant. Oh, that's not nice. Excessive memory grant dead. Excessive memory grant. Oh, the query had to wait 5 seconds for memory grant during execution. I did say I've got a memory problem. This is 2016 compat level. If I switch back to 190 to 2019, sorry, not 190. Memory grant excessive. Second execution. Memory grant on the second execution was 2 megs. As part of query execution, the amount of memory that was actually needed is recorded. Not the amount granted, but the amount that was actually needed. After the query completes execution, if the memory grant was too high, it is adjusted down. If it was too low, it's adjusted up. And that adjusted memory grant is saved with the query plan in cache. So no, memory grant feedback is not just 2019, it's 2017 and 19. I'm just switching back and forth between 16 and 19 compat mode because I've got a 2019 instance here. But this works in SQL 2017 as well. So it'll work in compat mode 140 and higher. Note the caveat here, saved with the query plan in cache. If you restart SQL Server, it's gone. If you clear the plan cache, it's gone. If you run out of memory like I'm doing, it's gone. It's saved with the plan. It's not saved anywhere persistent. It's not saved with query store. It's purely in cache. Right. So this is what you see in the execution plan. You'll see warnings on the first query, and you'll see the warnings go away in the next execution. Okay. Let me see if I can break this. I can definitely break this. So let me just try and force this. This should be now granting 2 megs of memory. Okay, cool. Let me go and change this parameter so that it's a stupid amount of memory needed. Ah, yes, I love slow queries. All right, this is showing me warnings left, right, center, and everywhere else. Warning, spill to tempdb. We wrote 132 pages to tempdb. The sort also wrote to tempdb, writing 244. If this was 2016, that would be there on the next execution. On 2019, second time I ran it, it's gone. So this was a demo of too low, and then sorry, too high and then too low. Now, there is a problem with this, and it's something I wrote a blog post on. If you've got a particular query pattern or particular pattern of querying your database, where you run a particular query with a parameter that returns only a few rows, and then a lot of rows, then a few rows, then a lot of rows, memory grant feedback will always be right behind where it needs to be, and will always be generating the wrong estimates. So the first estimate on this one was 4 megs, and it needed a stupid amount more because it's written up a whole pile to tempdb. Second time I run this, it'll go away. Yep, you'll notice the second execution, we've got 8 megs. But if I switch this back to 0 and then ran it, don't have the excessive grant, but I've still got too much. So do watch out for this particularly ugly case where you intermix queries that need lots of memory and little bits of memory. If you do have something like this, it's honestly better to split it into multiple stored procedures, and because otherwise memory grant feedback will just always produce the wrong results. So caveats on this: plan cache. If you run your query option recompile, it doesn't go into the plan cache, so no memory grant feedback for you. If you've got somebody from last century that puts with recompile on their stored procedures, that's not cached, no memory grant feedback for you. If you flush your plan cache every 5 minutes, I'm sorry, no memory grant feedback for you because it's gone with the plan cache. So it's very much dependent on a stable plan cache and a fairly stable querying pattern for it to work well. Okay, so requirements. Batch mode or SQL 2019? This adaptive memory grants works on SQL 2017, but only if the query is running in batch mode. 2019 removed that requirement. It now does row mode as well. The over or under allocate must be by 50% or more. So you saw that in the last example I did. This, well, not that one. I'm selecting, what, 70 megs of memory. That's a lot. If I switch this around quickly and see if I can get it to misbehave some more. Yeah, slow queries. All right, so we know that this particular parameter only needs less than a meg of memory, but in this case, it's been granted 8, and it's actually fine with that. It's not adapting. So there is a threshold. I'm starting to wonder if that 50% has been changed in a recent patch, because 8 megs off 1 meg is more than 50%. But there's definitely a threshold where it won't bother adapting. And in tests I've done, it will adapt 32 times, I think it is, and then stop. Because if it's adapting backwards and forwards 32 times, the query processor decides that this is an oscillating case where low memory, high memory, low memory, high memory requirements, and it's just going to stop adapting at some point and sit with whatever the last query had, which might not be ideal. So that is also a limitation. These numbers are not set in stone, the 32, the 50%. These are very much dev team reserves the right to adapt and change as they feel like it with patches. These actually may be wrong already on my demo, on my slides.
Gail, we have 2 questions here. Are there DMVs that show queries with frequent memory grant changes? Should we do anything about such queries?
Are there any DMVs? Yes, there are some DMVs that show the memory grant adaptations. If you do see those, yeah, you want to break them into multiple store procedures or in such a way that they get different plans. That way they can adapt their memories individually. So in my case, if I was frequently running this with 0 or 4, that is that oscillating memory requirement. One requires low, one requires high. What I probably want to do is split this into 2 store procedures, shipment totals by station priority 0 and shipment totals by station priority higher. That way they both get tuned on their memory grants. if they're important to you. If they're not, who cares? Yeah, you'd split the main query to two procedures. Yeah, because the memory grant adaptation's at the query level, not even the procedure level. So it's on this plan for this query. So two sub procedures would work perfectly, yes. Okay, yes, I'm reading the questions. I probably shouldn't be. Any other questions on memory grant feedback? Oh, no, I didn't want to restart Firefox. I'd go and look for the DMVs, but I don't want to restart Firefox at this point. So
Yeah,
go
the
documentation.
there's sysdm exec query memory grants per Elko. It's mainly the X event, as far as I know, from monitoring that.
Oh, yes. So, sorry, that's right. The DMV is just the memory grant. It's the extended event that tracks the memory grant feedback. Thank you. Yeah, I got that wrong. Is there a reason it doesn't use query store to persist the feedback? The dev team didn't do it that way. Feel free to log a user voice and ask for that. I mean, I've only been asking for it for, what, 3 years? They were thinking about it last time I heard. Okay, I think I have 15 minutes to talk about inline scalar functions. So, inline scalar functions. This is a 2019 feature. Everything else I've shown tonight has been 17 and 19, with the exception of the deferred compilation for table variables. But this one is entirely, absolutely only SQL 2019, inline scalar valued functions. So, in previous versions, scalar functions are, well, they're not inline, quite simply. A lot of people think they are because that's how front-end languages work. They're not. When you've got a scalar function in a query that is a call out to a different scope, different execution, return to the previous one, the function is run for every single row of the query that it's present in. This is horrible. This is absolutely vile. If you've got a slow function, it's horrible. It's absolutely horrible. I think I'm ranting about these things now. But seriously, I've had multiple cases where I've looked at client systems where they've said, we've got performance problems. I look at their code and go, yeah, I'm not surprised. Because they're either abusing scalar functions everywhere, or they're abusing multi-statement table valued functions everywhere. We've already seen the table valued functions. They're horrible, can be. Scalar functions, horrible. How do we fix this, says the client? Strip out all your scalar functions. But that's work, they say. So, yeah, that's work. Well, these days I can say upgrade to SQL 2019 and your problems will mostly be solved. Mostly. 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 I need to emphasize that. Mostly. So, scalar functions. I have a nice, simple little scalar function here. It's called date only. It strips the time off a date. I mean, how many of us use that kind of thing? Because converting to dates is hard. I actually need an extended event for this just to show how bad this gets. I swear I know where extended events are. I do not. Oh, look, I've got an extended event for scalar functions. Fancy that. I wonder why that's there. All right. I am in 150. Oh, I'm in 150. That's a problem. I can switch it to 140 at this point as well. This does not work. This inline does not work on 2017 either. So statistics time on, because I want an idea how long these run. There's a few thousand rows in the transaction table, like 30,000 of the things. Without the scalar function, 0 milliseconds of CPU time, 300 milliseconds elapsed time. With the function, 234 milliseconds of CPU time. So this has spent 234 milliseconds on the CPU doing, well, exactly the same thing, just the external call. And if we go and look at what, oh boy. Oh boy. I mean, they only run in like 3, what's that, milliseconds, microseconds. I don't know. I can't remember what the unit here is. I think it's milliseconds. But this thing ran 34,000 times. Must be microseconds. Ow. Okay, it's in microseconds. So these things ran maximum 17 microseconds. But the problem is they ran 34,431 times. Yeah. I hope you didn't want this result quickly. I mean, there's only 34,431 rows in that table. This gets really, really bad on larger tables. All right. Then we have this one. Oh boy. Yeah. This is not just a scalar function. This is one that returns data. Oh boy. So I promise you these two queries do exactly the same thing. This subquery here for total shipment mass is exactly what this scalar data accessing user-defined function is doing. All right. So I've turned stats IO and time on. I need to clear the filter there as well. Clear filters and clear the data as well. Let's see how bad this gets. Shipments only has a few thousand rows in it, so this should be fine. Executing, yeah, okay. That wasn't too bad. Note the orders that they've come back in is different, but that's just the query processor being the query processor. So for the first one, shipments, 1 scan, 254 reads, blah, blah, blah. Shipment details, scan 1, 2,955 logical reads, blah, blah, blah. 312 milliseconds of CPU time and 729 milliseconds of elapsed time. Yeah, that's not half bad. There are, how many? There are 34,000 rows in the shipments table. That's about right. Second one. So, does anybody see what's wrong with the IO stats here? This is when I love doing this in front of a live audience. People are actually looking and go, wait, where? Where? Where's shipment details? Because I did read from shipment details. I mean, this shipment mass queries from shipment details. The problem here is that the function is not in this scope. The function is running somewhere else. And so its results from stats IO are not there. So if you aren't familiar with this, if you don't realize this and you're looking at your execution stats, well, there's only 91 reads from the shipment table. This is a nice, efficient query. No, it's not. It's not at all efficient. Firstly, because we've gone from 300 milliseconds of CPU time to 2 seconds to do exactly the same thing. Just, whoops. Secondly, this one, unfortunately, does not, module end does not have the reads in it. So let me do this again and modify this particular extended event session. I want properties. What I want here is SP statement completed is the one I want. That'll do. So I'm going to clear that and I'm going to run this again. Okay, nice and efficient, still running, and now it's done. So let me filter by that one. Yep. We'll put the, that one. We'll put the statement into the table. And we'll look at the logical reads. That's not actually too bad. Oh, that's right. I put an index on this table. But this is doing 3 logical reads. Let me filter by that value as well. So the query against shipment details is doing 3 or 4 logical reads per query, 34,000 times. How many reads against shipment details? Well, let's say the average is 3 times 34,431. Yep. Copy that number. So this actually implicitly didn't say $34,431. So that's what it should have said. That's ugly. And that's just 34,000 rows and a query that had an index on it. I did a demo, sorry, I did some tests for a blog post a couple of years ago, left the function running while I went to get coffee, came back, looked at it, only one had finished. I was running it 25 times, went, watched some TV, had a shower, came back, only 2 more had run, went to bed, got up the next morning and 25 executions had only just finished. And the query without the scalar function, the absolutely equivalent query without the scalar function, had run in something like 5 seconds. 5 seconds to about 16 hours. Just by moving a subquery into a scalar function. So now I've made very clear how horrible these are. 150. Clear that. I want to remove all the filters as well. Right, scalar function 1, run both. 31 milliseconds of CPU time, 0. How many times did the function run? It didn't. Onto my data accessing one. 0 seconds, sorry, 1 second instead of 3. Note, shipment details is returned to my stats IO output, 600 milliseconds of CPU versus 300. How many times did the function run? It didn't. Inline scalar functions. The query optimizer, processor, one of the two, I actually don't know where this one is done, takes the contents of that scalar function and puts it into the query as a single object and executes the whole thing. This, the parser, thank you, Hugo. So it's done by the parser, the query optimizer. So it's like a view. The query processor, the query optimizer never sees the scalar function. The query processor never sees the scalar function. As far as they're concerned, it's just one piece of query. So fantastic. All right, here are the caveats. The list, okay, if anybody thought that indexed views had a long list of requirements, go and look at the requirements for inline scalar functions. Last time I checked, it was 1.5 pages long on my screens. It's also getting extended in every patch because the dev team keeps finding little things that they didn't realize. We've been getting this patched in every CU of SQL 2019. This will not be as fast as if the function was never there. And you can see that on this one, not that one, that one. The query without the scalar function was 300 milliseconds of CPU. The query with it was 625. It's still a long way from the 2 seconds that this was running in compat mode 130, but it's not going to be as good as not having the function at all. However, if you've got a customer that's got scalar functions all over the place, take them to 19 and up the compatible mode, and a lot of the problems will go away. This isn't obviously going to solve the fact that functions on columns are not saggable. That's, well, no, probably not. I haven't checked. But it's not going to fix it, but it seriously makes the problem a whole lot nicer. So 2019, Compat Mode 150, inline scalar valued functions. Okay, so that's adaptive query processing. That is intelligent query processing. In SQL 2017 and 2019, I think I've got 3 minutes left on my time, if my guess on the time is right.
You do.
Questions?
We have one right now that's in the queue. What is in the X event in the scalar function that you should?
Oh, that one. Originally, it was just module end. That doesn't double click, does it? So originally what was there was just module end. Nothing fancy. I had no predicates on it. I hadn't put any globals on it. It was just the stock standard module end, i.e. This look at store procedure completions, function completions. What I added to it to show you the logical IOs was the SP statement completed. This will fire for each statement that completes within a store procedure or function.
Not a tongue-in-cheek question from NZO. Is there anywhere you would actively recommend using user-defined functions in any form?
Sure, I actually love them for certain things. Don't do this with them. And think twice before you do this with them. But
my favorite
for something like
my favorite demo of this doesn't complete in 130 and runs in like 5 seconds in 150.
Yeah, I've got one of those. This is fine. This is fine. This is fine. Whatever. It runs once. Who cares if there's a little bit of overhead to it? It's when you put them into a query, into the select, into the where, heaven forbid, into the join of a query that you start getting problems, because that overhead of calling the functions happens again and again and again and again and again, once for each row in the query. If all you're doing is using it to calculate a variable in your store procedures, by all means, watch out for putting them in queries though. But if your query returns 5 rows and will only ever return 5 rows, again, who cares? The overhead's not huge. 5,000 rows, 5 million rows, yeah, you've got a problem then. It's a lot, same with a lot of things in SQL. They have their place. When you put them somewhere that is not their place, you get problems. Performance problems, typically in this case. Other questions before I annoy the organizers and go over time?
That's all we have for right now, I think.
Awesome. Cool. Let me kill the slide screen share. Well, thank you very much, guys. I hope everyone enjoyed that. I hope that was up to the level 400 expectations.
Yes.
Yeah, definitely.
I laughed a lot, Gail. You make me laugh when you talk. I love it. I mean, I learned something too, but like your sense of humor is great.
As long as you're laughing at my jokes and not at me, that's
yes, for sure.